Okay, now if you've here's our electrochemical series there. Okay, and have you seen before? The left-hand column, this one up here, that's all your potential oxidizing agents, and the best oxidizer is the top left because that is the most positive, got the most positive value. So it's best at sucking in electrons and accepting them, ripping electrons off other things. And on the right-hand side of the column, we've got a load of reducing agents. They've got the potential to go backwards and give out electrons. You can see the fluoride is a very, very poor reducing agent. It's got virtually no tendency to push away electrons because it's so positive. Whereas you go to the bottom of this column here, we've got potassium down there. That's a very good reducing agent, minus 2.92 volts. Very good at negative, very good at pushing away electrons. It's going to go backwards and form potassium ions. Okay, so that's the electrochemical series, and we're going to use it today in this video to answer some questions about vanadium. Okay, so we have got vanadium, transition metal. If you've done the transition metals section of the spec, you probably know these reactions already. Okay, vanadium can exist in multiple oxidation states. It can exist as +2, V2 plus ion, nice purple color, and characteristic sort of transition metals, colored compounds. The V3 plus ion, that's green. This VO2 plus ion, which is +4 and sky blue, and then this, you say it sounds the same, VO2 plus, but it's different. And the dioxo-vanadium ion, that's yellow, and that's in the +5 oxidation state. So vanadium can exist in all of those. Right, now the question is, if we add manganate, okay, we're going to add some manganate, MnO4 acidified, okay, we're going to add that to vanadium 2 plus, what, if anything, will happen? Right, so we need to look at, well, we've got a few different equations we need to be aware of here. So first of all, the half equation we're interested in is this manganate one here. And then we've got the V2 plus, where is that? That's down there. And then we've got other ones with vanadium. We've got that one's got vanadium species in it. And that one. Okay, so let's see what happens when we can manganate MnO4 minus. Can it react with V2 plus? Okay, so we're looking at this one and this one. Right, which is the most positive one there? It's quite clearly the manganate. It's very, very positive, isn't it? So that's going to be best at sucking in electrons, so that one is going to go forwards. This is the most negative, and so that one is going to go backwards. The V2 plus, yeah. That one will go backwards. So if you add manganate to this purple solution of V2 plus, you will oxidize it to the green solution, to this +3. Will that be the end of the story though? Well, it won't be, because look at this equation here. We've got V3 plus there. That is, the manganate equation is still a lot more positive than that one. So the manganate can go forwards, sucking in the electrons, and it can push the V3 plus one backwards because that's more negative. It'll give away electrons, and it will oxidize it to this nice blue color, the VO2 plus one, won't it? Is that the end of the story? Well, it's not, because we have a look at this one here. We've got VO2 plus there. What's going to happen to that? Right, that is still below the manganate one in the series, isn't it? So that's going to be pushed backwards, and the manganate to go forwards. So you're going to end up with that species, the dioxyvanadium, the yellow one. So it will oxidize it all the way up to there. So you can see how the electrochemical series is very useful, because all we did was we just looked at, and we can see what you've got our manganate up here, right, and that it can push anything, any of these, all of those, it can push them all backwards. The only one it can't push backwards is one above it, which is the fluoride ion. Okay, so we can see that we'll oxidize the vanadium all the way up to the +5 oxidation state. Right, let's have a little think now about if we had a weaker oxidizing agent, because manganate is a strong oxidizing agent, plus 1.51. Let's think about a fairly weak oxidizing agent, iodine. Okay, I2. Can I2 react with the V2 plus ion? What will happen there? Right, so I've got all my vanadiums all kind of highlighted already. I'll just worry about that. Okay, where's our iodine equation? Well, it's here. Can you see here? Okay, this one. Now, iodine, can it react with the V2 plus? Well, you can see, yeah, it will react with that because it's above it. Iodine can push that one back. Once it will form V3 plus. Can it react with V3 plus? Yeah, it can. It can because it's still above it. The iodine's up there. You push that one back. Can it then react? Can it push the VO2 one? Can it do that one there? This one? And it can't do that one, can it? Because that one is above the iodine in the electrochemical series. It's more positive. So if you add iodine, it will stop. It will stop at the blue color. You will get the blue color. You will not get the +5 oxidation state, the yellow color. So again, it's looking at what's above things in the series. Now this is getting a bit messy, but let's think about now a similar one. And the question is going to be, and this is one you're very familiar with, it's reactivity series of metals. The question is, which metals can dissolve in acid and release make H2 gas? Yeah. Right, so we need obviously do a bit of rubbing out here, I think. We are interested in our hydrogen electrode here, this one. Okay, a special one which is 0. Right, now that one, when can it go forwards? It can go forwards whenever it is more positive than other things. Okay, so it can go forwards and it can push this one back. It can push the iron one back going to Fe2 plus, and it obviously can do the zinc, the magnesium, and sodium potassium. You can do all of those. Which ones can't it do? Well, it can't push copper backwards, can it? Because copper is more positive. It's above the hydrogen in the series there, so it can't react with copper. Is there any other metals there? Well, you can spot silver as well. It won't do silver. So it's basically copper and silver that will not dissolve in acid, and it's because they're above that level in the electrochemical series there, because the copper electrode potential and the silver electrode potential are more positive than the acid one. Right, before we finish up, let's have a think about disproportionation. Okay, so if you remember what disproportionation is, it's when something oxidizes and reduces itself. So here, let's have a question. Will Cu1 plus ions disproportionate? So in other words, can Cu1 plus react with Cu1 plus? So for that to happen, we need to have one of the Cus as an oxidizing agent and one of the Cu pluses as a reducing agent. Where do we find oxidizing agents in this thing? We find oxidizing agents on the left-hand side, and we find reducings on the right. So let's find a copper 1 plus on the oxidizing side. Here we've got one there. See that one there. And let's find a copper 1 plus on the reducing side. Well, we've got that one there. Okay. Now let's look at those two equations I've highlighted in purple. Which one is the most positive? It's this one, isn't it? This one is the most positive. So that one will take in electrons. That's really good at taking electrons. It'll go forward, sucking in the electrons. And this one is the most negative, so that's going to push away the electrons and go backwards. So you can see if we combine those two equations, we get Cu plus and Cu plus. Well, one goes forwards and makes copper, and the other one goes backwards and makes copper 2 plus. So yeah, copper 1 ions, when you get them in aqueous solution, they will disproportionate. They'll turn into copper 2 plus and into copper metal. Let's just draw a cell diagram for that. So we could have, we've got our salt bridge. What's the rules? We put the most positive on the right hand side. So we put this one on the right, oxidized form next to the salt bridge, Cu plus, phase change, Cu metal, the reduced form. On the left, we put the most negative one, this one here. So that's going to be oxidized form is Cu2 plus. And here, it's in the same Cu1 plus. Now we haven't got any copper metal on this left-hand side, so we would need platinum in that. Yeah. It's only when you've actually got the metal element itself, and these ions are no good. They can't conduct electricity. They haven't got delocalized electrons. So you need platinum there. And what would E cell be equal to that? Well, E cell is equal to E right minus E left, which is equal to the right-hand side electrode. The most positive one is plus 0.54, 0.52, sorry. And the most negative is plus 0.15, so minus 0.15. So that would be equal to 0.37 volts. That would be plus, okay, that would be the E cell value for that one. Right, let's have another question about disproportionation before we finish up. Right, the next one is, let's get rid of this. Right, the question is, will Fe2 plus ions disproportionate? In other words, will Fe2 plus, or one of them act as an oxidizing agent on the left, and react with the Fe2 plus on the right, which will be a reducing agent. So this is beginning to look a right mess now, but I will, I think I will do it. I'll put it in so light blue, and that might show up. It's not working. Let's do it that way. Right, light blue. Right, which two am I looking at then? We need one with Fe2 plus on the right hand side. There it is, up there. Okay, and we need one with Fe2 plus on the left hand side. There it is, down there. Okay, so potentially, yeah, Fe2 plus could react with it. Let's see if they go in the right way though. Right, which is the most positive one? It is this one here. So this one is going to take in the electrons. So that one is going to go forwards. One goes forwards, or one always goes backwards. This one must go backwards, and that's going forwards. Okay, and it does because it's the most negative. It's pushing away electrons. So if we wrote a cell reaction for that, then we would get, we write down Fe plus Fe3 plus goes to 2Fe2 plus. So it's going to go in that direction. Now our question was, can it go that way? And the answer is no, it can't. It goes the opposite way. So iron Fe2 plus doesn't disproportionate, and you know it doesn't, because you can have solutions of iron 2, iron, and they're perfectly stable. Okay. However, on the other hand, what this does tell us, if you add Fe3 plus to iron metal, it will oxidize the iron metal to Fe2 plus. You can see there from the electrode potentials, that's why Fe2 does not disproportionate. Let's just have another quick practice of doing a cell diagram and all that, because they ask that a lot in the question. So in the exam, so let's say salt bridge, right hand side electrode is the most positive. Okay, so it's this one here. Oxidized species on the left, Fe3 plus, reduced on the right. They're both in this not phase change, they're both in aqueous solution. We haven't got iron metal there, so we will need platinum to conduct. And on the left hand side, we've got this one. Right, oxidized species is Fe2 plus, and reduced is Fe, and there is a phase change. We don't need platinum because we've got iron metal there. E cell, would be equal to E right minus E left. E right plus 0.77 minus 0.44. So that is going to give us right, mental arithmetic is not my strong point, so whatever that is there, yeah, it's going to be pretty positive. So that the iron will not disproportionate. There's another quick little tip. It's quite useful if you stick to the conventions, and the conventions are, of course, you must have one, your positive electrode on the right, and two, oxidized species next to the salt bridge. If you do that, just a quick check to show the direction of the reaction, you just draw arrows like that, and arrow like that. So that tells you Fe will turn to Fe2 plus, and Fe3 plus will also turn to Fe2 plus. Just a quick check. You're just checking that your predictions were right. Okay, so hopefully now you are pretty good at using this electrochemical series to predict which way a reaction is going to go.